Recording C. All right, I'll go over here. See if this is visible. There's one between you guys, that's okay. See if we actually, we'll just put it up here. Might be more clear. Yeah, it's not bad. All right. That's absolutely. Do you have just loose data, Lena, just like a raw data list?
Yeah.
Oh, let me grab that then real quick. So, friends, we're doing number, looks like number 8. Number 8 in the text. So I'm going to take a few moments and put the data in. Let's see, do I do that for 243? No. All right. Ooh. I'm going to be a little more efficient. I'm actually going to group this. 20, 30, 40, 50, 60, 70, 80, 90, 100, 10. The biggest one is 120, looks like it. I'll do a little counting. It's times like this where I long for Excel. For those of you on YouTube watching this, I apologize for the pause.
What did you put in 10?
There aren't 10, so I started at 20. I want 50. What the hell am I doing up here, friends?
You're adding the frequency count for the numbers on the L2 score, and then the L1 you're putting in the actual number.
Love it, Michael. Love it. Love it. When I looked real quick at the data, I shouldn't be talking and counting. I am Sean, after all, too. I looked at the data real quickly and noticed it was all multiples of 10. And I thought it might be easier to do it this way than trying to enter each one in. It might not be. It might actually be quicker to just laundry list them in. But this way, my eyes are over the data each time. So maybe it is, maybe it's not. 100, there are none. There are no 110s, and there are 2 120s, it looks like. I'm going to do a quick check. That's a 4 by
4 by 10.
10, 40. I'm going to do a quick sum on L2 to see if L2 sums to 40. Hot damn! So either I didn't screw up, or I screwed up uniformly. Let's pray that I sort of, what's that? I mean, 2, I believe. Yeah, 2. There you go. Thank you so much.
Your frequency listed
What the hell? Kidding. Totally kidding. Totally kidding. Totally kidding. So, Virginia, you ready? Starting at 20. It's 4, 8, 4, 6, 10, 0, 2, 4, 0, 0, 2. Decent? Yeah, decent. And so, often when we group data into distributions like this, we lose something from the data. Like for example, if we go from 10 to 30, and then 30 to 50, and 50 to 70, and so forth, we don't lose anything this way because the data is reported to us in 10-minute increments. Isn't that actually? So since the data is reported to us, we don't lose any accuracy whatsoever, rather than doing it this way or just listing them all in L1. So the first question is, can we claim that normality is, now normality, meaning what? Do we have a bell shape? Do we have an arguable bell shape? Because that's the big thing. I don't care so much about the sample size of 30. That number is fairly arbitrary, as you remember from magnitude 3 here. There's this magical number that gets used a lot. I'm not exactly sure why that has become part of the statistical collective conscious, but it has. It's more important that the data looks bellish. Because if the data looks bellish, that means the data looks t-ish. And the t-distribution is the one that actually makes sense to use for averages, because we're trying to do average workout lengths, I believe, Alina, in this one, average workout lengths. So how can we decide if it's bellish or not? There's something else I want to look at too besides just bellishness. But how can we decide if it looks bellish? Let me mute the screen. I don't respect my button with the remote. Just put it back here.
After you do this one.
How can I decide if it's bellish?
Graph it.
Ah, yeah, absolutely. Graph this thing. Graph this thing. Take a peek ski. So, quick graph in the TI. Second, y equals. And again, another reason why I love having the videos recording this is because now you've got the series of steps in the video as well. So second y equals, I'm going to turn two plots off, if it's okay with you guys. Two plots. Plot one, I'll make a histogram, and plot two, we're going to, actually this is already set up that way. Plot one will make a histogram, plot two will make a box and whisker with outliers to be shown. Because I also like to look at those. So plot one, let's grab plot one. It's on, actually this is exactly how it should be set up for how we put the data in. Assuming you put your data in L1 and L2 like I did. Did anybody put the data in raw, just a straight list of 40 data points? Perfect. Mary, Alina, how would your guys' lists read? What would be here? What would be here? The number one. Exactly the number one, because you use each one time. So again, keep that in the back of your mind. For raw data, if you just list, think back to 243. This isn't like a new thing, this is an old thing. In 243, when you have all your data just listed in a row, raw data or loose data as we called it, there would be X list or data list would be L1, your frequency would be 1, which means count each data point one time. Because I grouped the data into a distribution, you have to set it up like this. Use that for your data again, but use that for how many times to count each data point. This was the mistake the student made in 243 yesterday when he ran one of our stats. He ran one of our stats, but he didn't put L1, L2. It just looked at L1. And you, like I said, you could do that on your data right now. But it's only going to think there's like 8 data points. A 20, a 30, a 40, a 50, a 60, a 70, and blah, 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 blah. It's going to think it's uniform. This way, it knows it's not uniform. Cool? Set up good? Set up well? Well, yes. Pardon me. So back to second, y equals. Go to plot 2, and I'm going to slap a box and whisker plot on. A modified one. Make sure it's modified, that way you get the outliers as well. And this way you can see if any of the outliers are pulling the average one way or the other. You can see if they are or not. Make sure it's turned on too. So we're on, modified, L1, L2, yay, we like that. We like that. As far as the mark, change that mark to that. I like that one better, it's more obvious. So now we'll get a graph of the distribution. We can run the box plot, and we can see if we look Bell-ish enough. There's other tricks we'll learn in this class as we go too, but this is just an eyeball. This is just an eyeball. What's the quick and easy shortcut for getting to a good screen? Zoom 9. Zoom 9's really, really good. Okay, there's our stat. I want to mess with it a little bit. I want to mess with it as I often do because I'm me. This subdivides up into seven bars. Because the increments go from 20 to 120. Yeah, this scale of 16 is a little bit odd. I'm going to make this go to 130, changing the X max to 130. And again, the reason I'm doing that, the biggest data point was 120, right? 120. I'm going to make the bars 10 wide though. So essentially what I'm going to be getting is a dot plot, essentially. So the first bar is going to go from 20 to 30, which means it's only going to give me the 20s. Next one's 30 to 40, it's going to give me just the 30s. Next one, 40 to 50, the 40s. The last one that has to have 2 in it has to go from 120 to 130 to be visible. So that's why, it's one of those goofy little TI things. Okay, everything else I think we can leave, just press graph. Alright, so this is not bad. If you want, we can mess with the Y max a little bit to separate the graphs. Yes, no, maybe? No, Don's cool with it? Yeah, yeah. So you got your box and whisker up here. You've got your distribution down here. I've got an outlier over here, which corresponds, I'm guessing, to the 120s. They're a little too far above. I would second guess maybe using a t-interval in reality for this. We're going to go ahead and crunch it with and without those outliers to see what the effect of it is. But in reality, in practice, not in this class. In this class, if I give you those numbers and say, give me a t-interval, or more likely, give me the 95% confidence interval for the average amount of time they work out, you just go do it. But in reality, if you're outside of this, you have a whole project devoted to what to do right now. Your book doesn't get into it. Your book just says, are the assumptions for normality met? I don't know, it doesn't really look like a bell shape. I mean, it's bell-ish over here, but then we got this goofy little out, let's like, there's too much out in this tail. So we have a whole project devoted to that later, on what to do if you can't say it's normal. Go ahead, Michael.
Is it only not bellish because we haven't set it up by frequency?
We do have to set it by frequency.
Okay, gotcha.
Yeah, it's not bellish because we've got too much of a hiccup over here. It's almost like we get the bell and then we get the secondary little hump over here. So what I'd like to do, what is so the part A is, do we satisfy normality? No. I don't think so. It doesn't look bellish enough to me. What does part B ask us to do, Alina?
The next one is to find the confidence.
Do the 95% confidence interval for is it average number of minutes exercise per week or something like that? Good. So let's go ahead and crunch it, and if, with your guys' permission, I'd like to run it both ways. I'd like to run it with the outlier data over here, and I'd also like to pull the outlier data out and run it a second time and see how that affects our results. Is that cool if we do it both ways? Just more practice anyway. Yes, Susie?
Okay.
When you pull the outlier out, you're messing with your...
Careful. I love this. I love what Susie just said. She said, when you pull your outlier out, you're messing with your data. That is an extraordinarily good comment to make, but it's not the only explanation. It could be, I'm going to move this over here just a smidge, because this is a really good point you just brought up. It's right here in the middle. Okay. The reason I want to do it with or without the outliers, I see, if you will, normal behavior. But then I see this over here. My belief is that those two data points over there don't belong to this curve. They belong to maybe some other curve that's over here. In other words, this is a belief. I have no way of knowing how the data was collected. They could be sampling error. It could be due to the fact that they were collected incorrectly. Or they were self-reported. And somebody said, oh, they're this and they should be this. Make sure you can see this. There. So, the reason I'm going to run it both ways is I'm going to see if it does affect the average. If it doesn't affect the average, we say to hell with it. Leave it in there anyway. If it does affect the average, then I report to whoever I'm reporting to and say, okay, here's my interval with the 120s, here it is without. Notice the difference? How do we feel about those 120s? Where did those data points come from? Backtrack them, see where they came from. If they were measured correctly, it could be those people are doing something different the other 38 are not, and therefore should not maybe be treated. What was the population we're studying here, Alina?
That's cardiovascular technicians.
Cardiovascular technicians. Maybe those two in that 38 are doing something else in their exercise regimens that the other 38 are not doing. That gives them, for whatever reason, more of an ability to work out more minutes per week. I'm not saying throw them out just because they're different. I'm saying throw them out to see if there's some kind of another variable we're not looking at. The only variable we're looking at right now is minutes of exercise. There might be something else out there too. So that's why I'm saying, well, let's say anything else. Let's run the interval 2 times, with or without outliers, and see if there actually is a difference. If there's not a difference, then we say to hell with it. But if those guys, if those two 120s are actually pulling the average, let's see what we can learn from that. It's a very good point. Susie asked a very, very good question. Tossing data, especially data you've worked so hard to get, is never a good idea if it's not warranted. But if it is warranted, and you're actually giving us a nice segue for the rest of the course right now, checking to see if data belongs or doesn't belong in a data set. So let's run the T interval. So this is a 95% confidence interval for it is exercise times in minutes, right? I read that correctly? Good. For exercise times in minutes. So we're going to do it 2 ways. One, with the full data set. Where n equals 40. Okay, so let's crunch that first. Walk me through it. Where do I go to get this, my friends?
Stat test.
Stat tests.
And then
8 T interval. Now I know there's a simple answer to the question I'm about to ask. How do we know we're going to go to T interval and not 1 prop Z interval? And the simple question is because you gave us homework on the T interval. That's the easy answer. What's a contextual answer? I'm asking you to find the average workout time. So you know you're going to a T interval because we're asking for average workout time. Good, good, good. All right, This looks great. This is actually set up exactly as I need it to be set up for this problem. I've got data, L1 and L2, because I got my frequencies in L2. Some confidence levels at 95. Go ahead and calculate it, see what we get. Takes a couple seconds because that function is a little bit intense. So on average, we can claim, and I feel kind of silly. Well, what do you guys think about rounding? They were given to us to the nearest 10. Should we round to the nearest 10? Like, should we call that 50 and 60? Or do we call that 45 and 62?
Well, it's done in minutes of time of workout, so why wouldn't you just do it in the minutes?
I'm thinking of precision. The precision of the original data was only had one significant figure at best. So should I not worry about that? Just call it 45 and 62? Yeah? Okay, okay. So we have 45 minutes to 62 minutes. You're absolutely right, Michael. It's in minutes for sure. And I don't think going to 45.289 makes any sense.
Right.
But because the minutes themselves are only given to us in such a low precision value, it almost seems, well, what the hell? We'll leave it 45 to 62. Call it good. I'm not testing you in chemistry class here. All right. Let's go back and let's look at now the original data, which was here. Got the box plot up here with the outlier shown. Let's pull the 120s out. Let's have the hypothesis that we have an edited data set okay, an edited data set. So let's start by yanking the two 120s out. I'm not that upset about these guys right here. Because if I start drawing a bell curve, they actually come down and they get picked up in that bell curve that is kind of implied over here. If I'm assuming this is near the mode of the data, I can kind of live with that. It's these out here that kind of have me second guessing. So, let's go into our data set, our editor. Come on down here, remove the 120 and the 2. While you're at it, remove the 100 and the 110 too, because there's nothing in there. So now our largest data are 90 minutes, an hour and a half. Smallest are still 20. I think we should go back and do a zoom stat again to get a better window that actually fits, because we've lost a big chunk of the horizontal range. So zoom stat, here they come. Let's take these curves out, refit them again. Once again, I want to go finagle. I want to go change the data scale to a width of 10. Okay, so since my largest is 90, I'm going to set my X max. What do you think? To 100. You have to set it to 100 to actually see that last bar, and set the scale to 10. And this should be good. And just so you know, once you start finagling with the window screen, you press the window button and finagle with the window screen. What do you have to press next to see it?
Graph.
Very nice. Just graph. That zoom 9 is going to erase all the work you just did and replace it with. Yeah, I'm going to change the Y max just a smidge. That drives me nuts having the box plot. Hey, Brooke, I'm going to make Y max 20. Just to separate the box plot away from the rest of the data. I feel much better about this. It's basically the same bell curve that we had before. It still goes up and comes down. The tail's over here, out of sight and out of mind now. But the fact that that tail goes down implies that data out here should be outliers and should not happen all that often. Outliers should happen, according to one of the rules from 243, about 5% of the time. Roughly 5% of the time. We got 2 on that side. That side outlier should be 2.5% of the time, and this side 2.5% of the time. I saw 2 in 40 show up over there. My gut is saying that that's too frequently. So either there was a measurement error or something else is going on. Let's recalculate. I see no outliers indicated up here. Okay, it's the same box plot, except now there's not that little one dot out there. Let's recalculate our t-interval and see what it says. Go tight. All right, so we're back to t-interval. Exactly the same data set. Exactly the same setup, except now we have 38 data points versus 40. Let's calculate it. We now can be 95% confident that we have between 43 minutes and 57 minutes. And that's all we asked you to do in Part B. I'd like to create a Part C, if that's okay with you guys. I'd like to create a Part C. James is like, oh God, here we go. administered parts C, D through Z.
What happened to less is more?
Say that again.
What happened to less is more?
Oh, but the problem is that less doesn't answer this question. Did removing the outliers, is there a statistically significant difference in the exercise times computed with the outliers or without the outliers? Tell me why. The answer is no. There's no statistically significant difference. Tell me why there is no statistically significant difference, Jamie.
They overlap.
Because the intervals overlap. The fish, there's 2 aquariums set up. Let's draw the aquariums. Did the aquariums help?
Yeah.
Do the aquariums help? I hope they help.
Except when you're doing the test and then you ask for a reason, I'm really sure you're not.
Oh,
Because the
no,
fish
that
doesn't
one,
take
so what
it.
Susie's referring to is there's one question on the take-home exam where I ask you to verbalize, without using the aquariums, without using the fish, without using the word overlap, why the overlap and the fish in the aquariums works. Because what I found is, when I let students just continually say they overlap, the fish can't get in the tanks, got it. But I need you to know in the heart of the back of your mind what that's implying statistically about the variables. So I don't, on the exam on Thursday, please use the word overlap. Absolutely, use the word overlap. Oh my God, yes. But on that one question on the take-home, which you have another full week to do, by all means, explain what overlap means or lack of overlap means. I know what you're saying. I know exactly what you're talking about. So let's draw 2 tanks. Okay, the first tank, we'll draw a number line. Here's a number line. 43, I'm going to start down at 40. It looks like we go up to 62, we'll go to 65. So let's see, we go 40, 45, 50, 55, 60, 65. Okay, so we got 2 tanks. We got tank 1, which is the full data set. We got tank 1, which is the full data set. It goes from 45 to 62-ish. So this is with the outliers.
Where's the fish?
Well, the fish is somewhere in there,
Okay.
95% of the time.
Yeah.
That's the whole point of a 95% confidence interval. 95% of the time, the fish is in that tank. And the fish stands for what, friends? The mean of the... Yes, be brave. You kept getting quieter. It's the average of the population of all, I forget what the damn population was now, cardiotechs?
Yeah.
All cardiotechs average workout times in minutes. That average, that mu is out there somewhere. According to this, it appears to be centered on the center of this interval, plus or minus that margin of error. So we don't know exactly where it is, but the fish swims back and forth in that tank. The tank without the outlier shifted down a smidge. From here, 57 is here. This is without outliers. Okay? So we need parentheses. So we can't claim that there is a statistically significant difference in the times because the intervals Gesundheit overlap so greatly. They overlap immensely. Is it possible? Is it possible? Oh, go ahead, Michael, go ahead.
If they only interlap, as an example, if they moved to where it was like 25% of the data only existed in there.
Love this question.
Would
Love
that
this
change
question.
that answer?
The reason I'm using the word statistically significant,
Okay.
statistically significant is, if they touch at all, or if they overlap at all, you cannot claim that one is entirely above or below the other. In other words, you cannot claim they're different.
Because all the data might exist within.
Right.
Okay.
Michael's got a fantastic question. The question is, suppose the intervals look more like this. Suppose they look more like that. Now, as a percentage, there's more data as a percentage above this interval and this interval. But the problem is the fish lives in here somewhere and you don't know where. Furthermore, you can't apply that percentage because the percentage implies uniformity across the whole interval. And that interval itself, this is the one problem with the analogy of the aquarium. The interval itself represents a sampling distribution, which itself has a curve.
Right.
That confuses elements too. And that sampling distribution centered on a particular value can move left and right. And when you start looking at all those variables, you just say, the fish can be in the tank. And if it can be down here, it's possible the other one can be up here, which means even though this one looks on average like it's less than this one, it could be greater. That's when I talk about statistical significance. Lack of statistical significance of difference, statistically different.
So if they overlap at all,
At all, you can't be 100% sure, or excuse me, you can't be 95% confident of a difference. Or one, great point, by the way. Fantastic point. There are too many variables to measure. If they overlap at all, you cannot prove anything. And here's the problem. This is what happens. If you look at these two, not from a confidence interval point of view, but simply from a point estimate. For example, X bar in this one is 2 minutes below X bar in this one. So it can be claimed that cardio techs with outliers removed in our sample of size 38 have an average that is 2 minutes less than cardio techs of a sample of size 4 with the outliers included. But no news article will ever publish that kind of a statement because it takes too long to say and you can't tweet it. You have to say